In this example, we're going to be talking about H-Nmr, which is different from carbon NMR, so just H-Nmr. We're going to be working out this example here. So when we're doing H-Nmr, we want to focus on three different things. We want to look at the chemical shift, the integration, and the splitting or multiplicity. So the chemical shift is going to be probably like the hardest thing. Most of you guys should have a table that your professors have given you, and they'll tell you pretty much like the average values for these functional groups that we're looking at. So because we're looking at H-Nmr, we first want to figure out how many different signals we're going to see for these hydrogens. So looking at this molecule, there's no symmetry, so pretty much every single hydrogen is going to have its own chemical shift. So here's 3 hydrogens, so that's 1. Here's another 3, that's another. But then these two are going to be the same because single bonds have free rotation, so these bonds can reverse back and forth and they're going to have the same signal. Here we have 1 hydrogen, so that's another shift. So I'm just going to circle 1 shift. Here's another signal. There's no hydrogens here because this carbon already has 1, 2, 3, 4 bonds. This carbon has only 2 bonds, so we know we have another one, so let's make it a different shape. And then this one is going to be different. This is an oxygen, and then this is the last one, which is going to be different. So in total, we should have 1, 2, 3, 4, 5 signals for this molecule. So when we're looking at the chemical shift, we're first going to identify what kind of carbons we're dealing with. So this first signal is going to be a methyl group. Methyl groups typically have a signal around 0.9 ppm. So if you guys recall from our H-Nmr spectrum, we have, starting from the very bottom, we're going to have our 0 here, and it's going to get higher going towards the left. So this is going to be downstream or downfield, and these are going to be deshielded. Deshielded means that these electrons have more electronegative pull, so they're kind of more susceptible to the magnetic field that's surrounding them, so they're not protected as much because they're close to other atoms that are electronegative that's kind of pulling the electron density away, deshielding them. This is going to be upfield, and these are going to be more shielded. So 0.9 ppm is somewhere around here, and that's pretty shielded, so that's usually where we see our methyl groups, and this is of course ppm. So we're expecting these methyl groups to be somewhere there, but this is our carbonyl group, and we're 1, 2 atoms away from that carbonyl group. So that's pretty close, right? And oxygen's really, really electronegative, so that's kind of going to de-shield these a little bit, and it's going to move them more downfield. So we're going to expect this signal to be a little bit greater than 0.9 parts per million. All right, the next one is going to be this square. This square is what we call a methane group. So we have a carbon with only 1 hydrogen and 3 other alkyl groups attached to it. That methane group is normally around 1.7. But again, because we're so close to this carbonyl group, we're going to expect a shift larger than that, so more downfield. The next one is this little cloud thing. This is a carbon with 2 different hydrogens. We call that a methylene group. Methylene groups usually have a signal around 1.2. And again, it's very close to that carbonyl, so we're going to expect something more downfield or more deshielded. The triangle is also a methylene, but notice that this one is closer to the carbonyl than this one is, so this one should be more deshielded than this one. So when we're looking at an NMR spectrum, if we see signals, the higher signal should be for this one instead of this one. But it's still going to be greater than the 1.2 that we expect. And then the last one is a methyl again. So this methyl should also be around 0.9. This methyl is right next to an oxygen. Oxygen is electronegative, so it's still going to be that deshielding effect, so it's going to be a little bit greater than that 0.9. The next thing that we could calculate almost exact values for these, but most of the time we're going to be looking at an NMR spectrum that's already given us chemical signals. So the best thing that we want to do is kind of match what signals that we were given to the signals that we're predicting. So we should expect similar signals to this. Typically when we see signals that are close to the carbonyl, so 1 away from the carbonyl like this, we're going to add 2.5. So this methane group square, that 1.7, we're going to kind of estimate that we're going to add about 2.5 because it's 1 away from the carbonyl. Again, these are estimations because we're going to be matching these signals to actual NMR spectra, and nothing is theoretical in actual life. So 1.7 plus 2.5, let me just like do math because, so 12 and then 1, 3, 4.2. So somewhere around 4.2. Let's get rid of this. All right, these methyl groups are 2 away from the carbonyl, so we're going to add about 2. We call that beta. So this is the alpha position, this is the beta position. So the alpha position to a carbonyl should add about 2.5 to whatever the signal is. The beta position to a carbonyl, you want to add about 0.2. So we're going to expect this to be about 0.2 higher than it normally is, so about 1.1. This one is also alpha, so we're going to add the 2.5. So that's going to be around 3.7. This triangle is beta, so we're going to add 0.2, which is going to give us around 1.4. This is nowhere near this carbonyl, but it's next to this oxygen, and it's going to be alpha to the oxygen. When you're alpha to the oxygen, you want to add 2.5. So 2.5, that would be 3.4. So these are kind of the expected signals, these here. That would be your chemical shift. For integration, we want to focus on how many hydrogens are being represented per signal. So this is pretty simple. In this signal, right, this circle signal, we have 3 hydrogens here and 3 hydrogens here. So my integration would be the complete number of hydrogens. So 6 hydrogens I would expect to be seen for this signal. So my integration for this guy should be 6. So I'm just going to write here integration. And I want to put that right next to these signals. So I'm going to expect 6 hydrogens for this signal. On this signal, I'm only going to expect 1 hydrogen. So 1 hydrogen. My integration for this, 2 hydrogens. And if you guys are asking how I'm getting these hydrogens, all I'm doing is looking at the carbon. We know carbon's supposed to have 4 bonds. So in this case, carbon had already 2 bonds, so we have 2 implied hydrogens. In this case, it's the same thing. 2 bonds, so 2 implied hydrogens. And then here, 1 bond, so 3 implied hydrogens. That's it for integration, very easy. Normally, when you're looking at the NMR spectra, they're going to give you a value. So sometimes we're going to see these signals like this around there. They'll usually give you like a number up here. So for instance, like 2, or sometimes it'll be down here. That's just the integration. That's telling you how many hydrogens you have per signal. Then the third thing that we're going to look at is going to be the splitting or multiplicity. And this is when we use that neighbor rule. So it's n for neighbor plus 1. That's going to equal our multiplicity or our splitting. Okay. So for each of these, see if I can fit it over here. And I'm going to move this up here. So multiplicity. So for the first one, here, this was our signal. These are the hydrogens of interest. This is the neighbor. So for this, we only have 1 neighbor. So 1 neighbor plus 1 gives me 2. So I'm expecting to see a doublet for this signal. Doublet. That would look something, and again, this is like a 1.1, so let's put it somewhere around here. I'm expecting to see something like that, a doublet, 2 peaks. This one here has 6 neighbors. So that's expected to see a septet, so that's 7. But usually when you have so many hydrogens around the same area, we see what's called a multiplet. So you might not see 7 exact peaks. You might see kind of like this big mess of peaks. That's what we call a multiplet, and that's because these hydrogens are so close to each other. So this should have 7 signals, which we call a septet, but it might look like a multiplet. This signal right here has 0 neighbors, 2 neighbors, so 2 plus 1 is 3, so we're going to see a triplet. Next we have the triangle. So in this triangle I have 1, 2, 0 neighbors, so 2 neighbors, 2 plus 1, again a triplet. And then lastly we have this signal here, and this signal has no neighbors, so 0 plus 1 is a singlet. Okay. So now that I've looked at all three of these things, I could actually compose my own little NMR spectrum, and hopefully that would match whatever it is that I would find if I actually put this into the machine and it produced the spectrum for me. And that's it.